morning, everybody. My name's Paula. I've been programming Clojure for the past 12 years. And most recently, I've been doing a little less Clojure in my day job, but I still like to do it in my evenings and weekends. This talk, so I live in the United States. I'm originally Australian. And if I seem a bit vague, it's my jet lag, and I apologize. This talk today is a combination, really, of some technical background for a library I wrote, and also the story of how it developed and ended up as a part of ClojureScript. So this all began back in November last year, so nearly a year ago. Alex Miller made a post on Clojurian Slack where he said that the Alpha 3 had just come out for Clojure 1.11, and one of the things which had been introduced was a new Clojure.java.math namespace. These are really just wrappers around Java-lang math. But a lot of people using these functions in Java-lang math would often not call them in the most efficient way, and it was a really fundamental part of the system that people were not necessarily getting the best use out of, and the Clojure core team believed that providing native support for getting that right was really going to help people. So there's a lot of inlining going on. There's also the function wrappers, so you can pass these functions around for things like map, and you know, there was some real utility to having this. However, I was a bit concerned and frustrated because one of my projects is a database which runs both in the JVM and on browsers and on Node, and in that case I was writing a lot of code which would be conditional compilation between ClojureScript and Clojure. And now in my new job, I even use conditional compilation to CLR. And having to write similar code for these different platforms is always very frustrating. Of course, it's error prone. And I really like to see the benefits of a standard library across all platforms. So I asked Alex about this. And he said, well, you know, there are issues here. There's a lot of guarantees that come out of the JVM methods. Can these be met by JavaScript's notions of numbers? He said, if possible, if you can do that, then yeah, maybe we could do that. But on the bottom there, he's pointing out that the goal here was to expose the Java-lang math, not to make a math library that's portable. I see where he was coming from there, but it was really important to me. So I went aside and started researching what this involved. Now, if we look at JavaScript itself, JS math has a number of constants in it, e, pi, log10, log2, and then, let's see, log10e, I can't recall the difference between, oh, base 10, log10 and log2, etc. We've also got a square root of half and square root of 2. And then we've got this list of functions, which looks large. It certainly intersects a lot with Java-lang math, but it actually doesn't have all of the functions in Java-lang math. And the bigger the divergence between the two platforms, the bigger a job this would be. But a lot of the basic stuff, trigonometry, hyperbolic trig, the logarithms, these things are all pretty fundamental and they're available. But what about the guarantees that Alex mentioned? Well, in JavaScript, all numbers are floating point. Yes, even all your integers are floating point. They're represented with 64-bit IEEE 754 floating point standard, and This is actually common between the JVM and JavaScript. Within that standard, there are a couple of variations that you can have, but JavaScript has adopted exactly the same options for a 64-bit standard number. Mozilla documentation does, however, mention that there's a precision which can vary from one platform to another. I did some investigation with this, and my experience was actually that the numbers typically calculated out to be identical. However, when they were printed, so when you look at them, often the final decimal, the final decimal place would be, one digit out from another, or it might be, one digit longer. But the numbers were often exactly the same, even when the display was different. So I got back to Alex, and I said, well, it complies with 754, including the full bit representation. There's a few functions missing, but I'm sure I can do this. And I'm sure because other people also expressed interest in this, they're probably doing it as well. So Alex then expressed interest, saying, yeah, if it works out, then he'd be prepared to consider changing that namespace from ClojureJava.math to ClojureMath. So what is IEEE 754 64-bit? There's standards for other lengths as well, but this is the one we're interested in. We have a 64-bit number. The most significant bit, way out on the left there, is the sign bit. If it's 0, it's a positive number. If it's 1, it's a negative number. The next 11 bits are the exponent value, and this is a biased value rather than a 2's complement for negative values, and I'll get to that. And then we have a 52-bit significand. The majority of your number is stored there, like all of the precision that's going on, and the exponent just says, well, where the decimal point's going to be in all of that. Within this standard, and I'll get to how standard numbers are displayed very soon, but we've got 4 special groups which aren't the same as the other standard numbers. The first one is 0. And as you can see here, it's all zeros in every position, except the first one. It's possible to have both negative and positive 0. Now, Java displays this. JavaScript at a node REPL will display it, but if you say print it, it'll print a negative 0 simply as 0. In ClojureScript REPLs, we only ever see 0 even when it's negative. But investigating what's going on under the hood, we'll find that it's a that it is still recording the fact that it's a negative 0. We also have infinity. Infinity has a completely 0 significand, but the exponent is all set to 1s. And again, we've got positive and minus infinity. We have not a number, which is similar to infinity. The big difference, though, is that somewhere in the significand, we have something which isn't 0. So any bit there is non-zero, you have a not a number. The very top bit is what's called signaling, and it seems that other systems will use this. So if you have a signaling not a number, that'll often show up as an error in your system, whereas a non-signaling not a number will be stored and returned as not a number. JavaScript tends to show up not a numbers a lot of the time, so we're not seeing signaling values show up in JavaScript. This non-zero area is used in some systems, not JavaScript to my knowledge, to hold information about errors which may have occurred. And finally, we have subnormal. For very, very small numbers, they behave slightly differently to all the other numbers which can be represented. Subnormals are when your exponent is set entirely to zeros, and you're not a 0 number, because 0 is the smallest thing that it can represent. So 0 is kind of like a special case of subnormal. But in the general case, how do these numbers work? Well, consider the number 1, 2, 3, 4, 5. It has this binary representation. It's a positive number, so we can set the sign bit to 0. And the rest of the number, we can think of it as 1.1, and then continue with the rest of the string, by 2 to the power of 13. Now, because we don't need to consider all the leading zeros which might appear in a number like this, we're only interested in that very first one and where it appears. That means the number always begins with a 1. And so we can actually ignore it. We don't need to store that first one. And so consequently, only everything after that decimal point is included, and the first one is implicit. So that's what goes straight into the significand. The rest of it will all be zeros. And now we've got our 13. Well, we need to have that exponential bias. In this case, both JavaScript and Java use a bias of 1023, and that's halfway in this space that we're looking at here. And so that's 13 plus 1023 is 1036, and that's the bit pattern that comes out of that, which results in the significand going there. And you'll notice that numbers which are close to 0 are really just around 1 followed by all zeros. If you have an exponent bias, if you have an exponent of 0, it'll be 1 followed by all zeros. Negative numbers are smaller than that, positive numbers are larger than that. And this allows us to have non-two's complement arithmetic going on inside of the exponent space. By not having the two's complement arithmetic, we have the same number of positive numbers as negative numbers. Okay. If we want to consider the full range of integers, and this does come up in the library, we're going to need to see, what the range will be. We can go from all ones with a negative sign, and that would be the minimum possible integer that you can have, or all ones and a positive sign, and that's the maximum integer. So that's 2 to the 52 bits that we're representing, plus that one implicit bit at the beginning. So that's 2 to the 53. And then we take away 1 because that's how these numbers work. And these are the largest and smallest integers that JavaScript can possibly store. If you go any can safely store. If you go any larger than that, now all of a sudden you've moved in outside of the space which can be fully represented, and you'll see initially that numbers, if you increment by 1, nothing will happen. If you increment by 2, it'll happen a couple of times, and then nothing happens until you increment by 4 or by 8. And that's as your powers go up and you start sliding into a space that can't fully represent all of the integers. Okay, so we want to do bit manipulation in JavaScript under ClojureScript. How are we going to do that? We've got a 64-bit number here. Well, we can break it up into two 32-bit numbers, a high double word and a low double word, and these are terms taken from C. Or we can break it up into bytes, and we can go with a little endian format. The reason I'm going with little endian here is that all our popular chips today are using little endian notation or representations. And so that's Intel, let's see, some of the older chips, I used to use Sparks quite a lot. They were big endian, but I'm not finding this on any popular systems at the moment. However, I did not want to make the presumption and for it to fail for somebody somewhere, so I actually do test, and that's done simply by storing numbers in an array and saying, what order are you in? Okay, so we want to take our 64-bit numbers and turn them into bytes or double words. How do I make that cast? In C or C++, it's easy. In JavaScript, I'm using a different approach. I'm creating an array buffer which is large enough to hold all 64 bits. So that's an 8-byte array buffer there. Then I'm going to create a double array and a 32-bit integer array, both of which are backed by that same array buffer. And that means that if I'm accessing what's in either of those arrays, I'm accessing the same bits in the machine. The high offset, I look up this, this flag that I've set, little endian, to say, well, is the high one at offset 1 or at offset 0? And then I take my 64-bit floating point number and I write it in to the float64 array, and now I can get the high word and the low word just with some simple array gets. Similarly, to update a 64-bit number, I can just do an A set. Okay. I had a discussion with David Nolan about this. Older systems don't support array buffers and having arrays which are backed by them. David had some concern about this, and we had a long discussion about it. The problem with trying to do bit manipulation on these numbers without this sort of trick is that 64-bit numbers floating point numbers get normalized down to the standard representation. There's not a lot we can do with them safely without changing the exponent when I really just meant to change the significand, that sort of thing. There's not many options here, and finally David agreed that this was the only way to do it. Fortunately, we aren't seeing many systems which don't have this. It's really much older JavaScript systems that don't support this. So, 1 hour, 8 minutes, he finally agreed. And I had to go through the whole process, and he accepted it for me, which I was grateful for. So what do we have here? We've also got bit operations, because we're getting these bits out. What are we going to do with them? Well, we've got bit and, bit or, bit shift left, unsigned bit shift right. These all sound quite straightforward, except on JavaScript, because we've got this limited space of 52 or 53-bit integer numbers to work with. That's a little awkward to use with these sorts of operations. What does JavaScript do? It decides that only the bottom 32 bits should be used when you're doing bit operations. So it implicitly converts to a signed 32-bit number. Note, I said a signed 32-bit number. So while I can have 53-bit integers, positive and negative, once it truncates it down, it's really a 31-bit number, positive or negative. So let's say I want to convert this number here, 4AFE and 0. So that's a 32-bit number. And if I OR that number, that's decimal representation of the same thing. If I OR it with 0, I get the same number. That's what I expect. It's great. But what happens if I go to CAFE? That's the same number, but now the most significant bit has been set. So it's 2 to the 31 larger. And I get a negative number come out. Okay, what if I set the next bit going up into the 33rd bit now? I'll go back to 4AFE once more. And I'm back to the first number. So in each case, these are getting larger and larger, and I go from a large positive number to a negative number, back to the first positive number again. So it's truncating it each time, and it's treating that first bit as a signed bit. And we have to be careful of this sort of thing. An example of where we want to be careful are signed comparisons. Now, all comparisons are signed. Is this bigger than that? Well, you just saw I had a larger number and it's going to come out negative. So to do that, I've got this unsigned comparison operation, less than. And the way I do that is I pull out the top nibble and I compare that first. And only when that's the same, I then compare the remaining bits of the system, the bottom 28 bits. And I could have done 1 bit followed by the remaining 31 bits, but it just felt more efficient to do a nibble. Okay, so then doing these implementations, what are we going to end up with? We've got some operations which were really simple. Doing something like sign, it just does a wrapper. Most of this is actually just documentation on what it's doing. And I copied a lot of that documentation out of what Alex had in Clojure.java.math. But I did add in some extra options, like if A is not a number, or negative infinity or positive infinity, then we're going to get not a number out. And I had to check that Java's sign actually does that, which it does. But you'll see at the bottom there, it's just calling through to JavaScript's math sign function. Let's see, implementation range, range checking here, same sort of thing, but now Java's behavior is a little bit different to JavaScript's behavior. So I had to specifically check. If it's not a number, I'm going to return 0. If it's finite, I'm going to round it. If it's infinite, I'm going to return the maximum safe integer, and otherwise I'll be returning the minimum safe integer. That's because we're going, it's different sort of values that we were getting back for those edge conditions. And then I had some functions which were a relatively simple re-implementation. In this case, I do a couple of range checking. Is a number within the safe bounds? If it's not, I can throw an exception. In the case of Java, it does the same thing. If you're doing this on integers, for instance, as opposed to longs, then if you have a number which is in the long range, it'll say, oh, it's not within range, and it'll give an error. Anyway, I mostly just use basic math operations for that kind of thing here. So this is all fine. Then we get some where we really do need to delve into those bit operations. In this particular case, it's the ULP function, unit in last place. And this meant learning a little bit about what these functions were doing, why and how. And so I ended up re-implementing all of that using these bit manipulation techniques that I was talking about earlier. So these sorts of functions, a little bit extra effort, not a big deal. Then we get to functions like IEEE remainder. These things were scary. What I'm showing here is partial code from the JVM. JVM's been GPL'd. So I could use that as reference material. I couldn't copy it because it was GPL'd. I couldn't even transliterate it because I don't want to run into any sort of legal issues. But I did want to use it to understand, see if I was doing the same kind of thing. Am I getting it right? Well, this is how it looks here. A small slice out of that function, it finds 2 integer log operations on numbers. And this is all C code, which is called through the native interface on Java. Doing the same thing in ClojureScript, I extracted it out to a function, and this is essentially equivalent code. The constants, for instance, that hx is less than that particular constant, you'll see that that occurred in both of those cases there. And I could call, ix and iy were going to be set to calls of this particular function. Going on further in that function, we have blocks of code which in C look like this. And I looked at that and whimpered. But it was 1 a.m. and I thought, what the hell, let's go for it. The equivalent ends up being this. It didn't work. I ended up having to pull it apart. I pulled apart the Java code, the C code, and ran that, compared it, and then I discovered that the IEEE remainder function, I was calling it and it didn't put any of the debug statements that I'd put in or anything. I couldn't follow. until I realized that Java has just re-implemented codes which is in glibc, and I was accidentally calling the glibc stuff. So these functions are all in glibc, but for some reason Java has decided to implement all of their own, and it's almost the same code. I did go to each project and compare them, but this less than operation here, this one caught me out. There were some very, and this one here, very tricky things showing up in the loops, and those less than operations only came into effect if that one bit partway through my number was set, which meant that a lot of the time numbers were working, and then every so often a number wouldn't work. And I'd have to trace through and discover what was going on, and discovered, oh, it's doing a comparison, and even though this number's larger, it's signed when it's at 32 bits, and therefore it's smaller. It all got very hairy. Okay, once I had it all going, how do I compare it? Well, I thought my first step ought to be testing on the JVM. It's the same code in Java as it is in JavaScript. Sorry, what am I saying? It's the same code in Clojure as it is in ClojureScript. So I ought to be able to run this ClojureScript code in Clojure. So everything becomes a .cljc file, and most of what I'm doing should be portable between the two platforms, and then I can compare it directly to Java-Lang math. More importantly, I can use generative testing to do a lot of the work for me, find all of those edge cases. One problem though is I'm going to need stubs for the JavaScript functions and symbols. So for instance, if I had an expression like this, JavaScript is finite with calling it on the JavaScript number max safe integer. Or if I'm calling the function JavaScript is not a number on positive infinity. You know, how do I get code like that to work on Clojure and not just ClojureScript where it's native? Well, to do that, I created these testing stubs in Clojure. So the namespace itself is called JS, and that means that, you know, if I see JS, it doesn't treat it as a magic thing like it does in ClojureScript. Instead, it just sees this namespace. And then I have these constants just with number on the front, and that works too. So now I've got the functions like is not a number, is finite, is integer. This all works quite easily as pass-through. But what about those buffers? Now, I could possibly have done some of this with records, I'm not sure, but I generated classes to do this. For a start, I created this thing called array access because when I'm talking to these classes, the only way I talk to them anywhere in the code is with aset and aget. So that's what I've added to this array access protocol. And then I have these 4 classes which I've generated. The first one is the array buffer, and that's going to contain the array, the backing array that everything else gets wrapped over the top of. And then I have a byte array, a 32-bit int array, and a 64-bit floating point array. Implementing them, the array buffer itself starts out as just a byte buffer allocation. And then these constructors here are simply wrappers around the byte buffer. In the case of the byte array, I just ask for the buffer. In the other 2 cases, I ask for the buffer and then I store them as an int buffer or a double buffer. And that's simply a view for the same data. It either looks like 32-bit integers or 64-bit floats. And then I can extend that protocol onto each of those classes appropriately. So aget, just pull something out of the buffer here. Aset, I need to ensure that I'm getting my sign correct. It's expecting integers to be sent as the value that goes into that byte, but it will truncate it down to just 8 bits. So I need to make sure my negative numbers are being set correctly. And the same happened with 32-bit numbers, and 64-bit buffers were quite simple because they just go in and out negatively just fine. So I started running the testing, and I immediately hit a problem with the generative testing. If I generated just a few test cases, everything was going fine. So I let it run, and then I had this one pop out. In fact, I had several come out. That was the first of them. This number, if I do a mod of this number for that, which normally you do a mod the other way around with a large number and you're doing modulo something smaller, but okay, I want to find the floor mod of this. I get back 1, but I shouldn't. I should have got back this number down here. You'll see it's just 1 offset from here. Why was this not working? I tried calling it directly from the REPL, worked fine. But in the generative testing, it didn't work. Turns out, Clojure itself had a bug. It's actually, there was a bit of debate over which ticket was the best one to address it. But what was happening is that the compiler is non-deterministic in selecting the appropriate math function out of Java lang math. Sometimes it would be picking the function which accepted integer arguments rather than long arguments, and it was truncating this number to 32 bits. And yeah, I think it truncated to 32 bits to be something quite small, and doing that modulo 1 ends up being 1, and consequently we, this is where the error was coming from. This has been addressed in more recent versions of Clojure. But in the meantime, I got around that just by doing an explicit cast along, and the compiler sees that and picks it up correctly. The whole process took 4 or 5 nights, I think, getting everything right. And I got back to Alex, and I spoke to him, and yeah, I said, I think I'm confident about this. I'd nearly finished at this point, but I was close enough to the end. I'd already done the IEEE remainder function, which stretches over several functions. Once I had that done, I was confident I could do the rest of it, and I could. It turned out that was the hardest one. Anyway, I was confident that I could do everything in ClojureScript. Alex said thanks, and shortly after that, he was prepared to change the namespace, and we did see that come out. So then Mike Fikes gets in touch. So I've been talking on the ClojureScript dev Slack, and Mike jumps in with this suddenly one day, and it's like totally out of the blue. So he'd obviously been looking at it, and he had lots and lots of suggestions in here. Some of these were stylistic, some of these were about efficiency, some of these were about memory usage, but there was a whole lot of stuff going on. 1 or 2 of these things actually turned out not to be a problem, and we had long discussions, and I got to know Mike much better during this time. Now, in terms of what's being generated, I did not know about this, but he pointed this one out to me, and I thought I'd pass it along for anyone who hasn't seen it. If you're using ClojureScript and you say that you want to set print function bodies to true, you define something like, in this case, XOR. When you just type XOR at the REPL, it will print out the JavaScript that was generated when you defined your function. This has been such a lifesaver for me. I use this all the time in all my ClojureScript code now. So we got through to December 10. This is, what, 2 weeks after the original announcement? And I said, I have ClojureScript Math at a point where I'd like to propose it for inclusion. I was really scared. I didn't know how this would go over. Like, are they going to rip it apart? Are they going to say, no, this doesn't belong in ClojureScript? Or, is it going to be its own library, or does it actually get into the language? But I was hopeful that it would. I knew that there had to be some cleanup, that it had to integrate in a little better, but you know, I thought I had a decent shot of getting it in there. Once I got to that point, I had to start looking at what's the JavaScript framework for doing all this generative testing. And, you know, in particular, if I was going to use generative testing, can I compare what's happening in the JVM to what's going on in JavaScript? Well, I needed an NREPL that I could get to from, a ClojureScript NREPL that I could get to from the JVM. And if I was going to do that, everything has to go over strings to that REPL. And that's when Mikhail, if he's in the room, contributed here. He wrote this block of code for me, which sets it up and gets it going. And I had been looking at other options, but when this had just been passed to me, why would I not just use it? So I did. But the generative testing got a little hairy. I needed to have a reusable way to be able to send a whole lot of numbers in, get a whole lot of numbers back out, compare it between the two platforms. So I created these macros to do it. I've got several macros, but this is an example of one of them. This tests functions which take a type and return the same type. And there are also functions which take two of one type and return one of the same type, that sort of thing. But in this particular case, what it does, it starts off by actually generating a sample set of data. And then it converts that into a sequence. Oh, sorry, it is a sequence. It converts it into a string of all of those numbers. And you'll see that it does print string on each of them, turns them into double, and then maps CLJS math / whatever name I've given it across each of them. And that's mapping the function over each of the doubles. And now we're saying, let's do the same thing in the JVM, except we're already doubles. We haven't needed to convert to a string at all, so we can just map the function directly. And then we do the compare. So we're mapping equality across both sequences of results. And an example usage of it is taking a double and returning a double, having a function that does that. And then the arguments here are things like how many, n is how big a sequence to work with. JFN is the name of the Java function. CFN is the name of the ClojureScript function. Gen double is the generator to use. And equals is the operation to apply. And that needed to be done, like we needed to apply our own operation because sometimes equality doesn't cut it. For instance, if both sides are going to be not a number, we want that to return true. If they are equal, great, return true. If they're not equal, let's print what the difference is between them before doing a comparison within a delta. And then I do this a couple of times with different tests. So with signs, I actually gave this as a string for saying, well, here's the variance on sign. And sign, cos, they do show up occasionally as having a slight variance. Okay. I'm running out of time, but also I've got a little bit of a buffer. Okay, so I asked David, like, is this all looking good? And he's very nice. He said, yeah, that's actually perfect. He's thinking maybe we could use this in ClojureScript. So I'm hoping to contribute there to see that come back up in other uses. So then the process, if you go onto the ClojureScript pages, they actually describe how you're supposed to create a patch, how you create a ticket and attach the patches to the ticket and work through it that way. And there's a particular format that you do need to follow. And if you don't, you'll be instructed on how to do it and get it right. We needed a ticket to hook it up to. And so, when I snapshotted this, it was closed and fixed. But this was the ticket we were working on to get it going. And then finally, David announced, that or announced within the ClojureScript developer list that he'd applied it, the patch, it was now merged in, and of course, everybody was happy. It then took months before the next release of ClojureScript. I got bored, I created new tickets. It turns out that ClojureScript 1.11 was missing all of these functions that Clojure had introduced. So I went ahead and did those. Some of them, like things like nan, infinite. I knew how these things worked now. So I went and did all of that while waiting. And then we finally had the release back in May. And yeah, we've got parity across ClojureScript and all of these other functions that I did while waiting impatiently for the release. And yeah, that's the final step. So thank you very much, everybody. And if you've got questions about this, or the process or the code or anything, I'm happy to answer them.
First of all, cool. Wow. Second of all, so some of these functions in JavaScript and also in Java are backed by compiler instructions or machine code. So how is the performance comparison between ClojureScript implemented functions and calling native JavaScript math operations?
They're all of these functions, I didn't run criterion across them, so I don't know the actual answer to your question. All of these functions are like very close to like sub-millisecond. It's really hard to say. What I can say is that working through the process with Mike Fikes, I saw a lot of the JavaScript that was being generated, and essentially it came out to the best JavaScript we were going to get. I couldn't write the JavaScript by hand to be any faster than what we were getting. So the fact that it was ClojureScript and not, say, implemented in JavaScript under the covers, well, if it had been implemented in JavaScript under the covers, David Nolan would not have accepted it. I believe he wouldn't have accepted it. But you know, doing it in ClojureScript turns out to be fine. It compiles really nicely if you pay attention and you follow the various hints and you have Mike Fikes helping you.
Impressive work and great talk, thank you. I was just curious, what tools have you used to see all those numbers like under the hood and like what's happening within JavaScript, and like how did you find out?
I used a REPL.
Just a REPL?
Yeah, I wrote functions which would take a number and then print it out as binary. And there's operations in JavaScript to do that. You can say that you want toString and give the base that you want to use. So just use a base 2 and it'll print it out. And oftentimes I wanted to pad that with zeros so that I could align everything. So I'd use those. Sometimes I wanted to type bit patterns in and you know, it would be easier if I could like copy and paste the bit pattern. And so I had things which would load binary numbers up for me, that kind of thing. I work with hexadecimal quite a bit, especially my Asami project, storage on disk. I'm working with bytes quite a bit, and being an electrical engineer, I've got a background of reading hexadecimal, so it wasn't that problematic for me. But yeah, between functions for convenience and the REPL, that was all I used, yeah. Well, no more questions. Thank you very much, everybody.